everyone, my name is Jordan McKaig, and I am a PhD candidate at Georgia Tech. I'm working with Dr. Chris Carr on using solid-state nanopores to detect biosignatures and think about potential for agnostic life detection. So throughout our universe, or throughout our solar system rather, there are a variety of planetary bodies that have conditions thought to be hospitable for life. So things that are in the middle of this Venn diagram containing the right raw materials, energy sources, solvents, and climate conditions for living things to possibly persist. Many of these environments are aqueous and saline environments. And as we've discussed previously, today and yesterday, salts have a major influence on the ability of an organism to live in an environment, as well as the potential for biosignature preservation. And I'm particularly interested in how salts can interact with these biomolecules in terms of doing detection with nanopores. So specifically the biosignatures that I'm interested in are nucleic acids and ribosomes. Nucleic acids, that's your DNA and RNA. It's a linear charge polymer that is responsible for storing and regulating genetic information. Ribosomes are cellular machinery that translate this information into usable proteins. Nucleic acids and ribosomes are ubiquitous to all known life and are part of the central dogma of biology. So this is a paradigm in biology that traces the flow of information from these charged polymers of DNA and RNA through proteins. So it's been proposed that molecules of similar structure and function, but different biochemistry from some of these things could actually serve as evidence for life as we don't know it. In 2017, it was proposed that linear charged polymers with repeating units, analogous to nucleic acids like DNA and RNA, could serve as an agnostic biosignature. And we are also working on a paper arguing that translation-performing molecules of a quantized size, analogous to ribosomes, could similarly serve this function. Since these don't have the same biochemistry of life as we know it here on Earth, it would require detection with a method that doesn't necessitate any specific chemical composition, which leads us to solid-state nanopores. This is an agnostic mode of detection, which requires a molecule to be suspended in a conductive solution. So your nanopore here is a nanometer scale pore that's drilled into a membrane. A current is passed over it, and a voltage or a pressure differential drives molecules through the pore. As things go through, these translocations create blockages in current, which can be used to get information about the biomolecules. And I just want to highlight, again, this does not require specific biochemistry, making it exciting for not only investigating living things here on Earth, but also potentially elsewhere in the solar system. So what we did was show a proof of concept for something called the Ontera nanocounter, which was a proprietary solid-state nanopore instrument. And these are all of the different biomolecules that we analyzed, including some DNA samples, RNA, and ribosomes. And if you'd like to hear more details about how specifically this went down, please come talk to me at my poster. And then also I have some of the example results. So first we have a few graphs showing just different example events with signature-specific events for each biomolecule structure, and then some heat maps showing the change in conductance and the dwell time for all of the events in a specific run, and then some overlaid samples of what all these events looked like. And what I just want to highlight here is, let's see, do I have... Okay, great. I have overlaid DNA events all here in the blue. This is a circular plasmid, so just a circular piece of DNA. And it is a pretty short dwell time, but also a much larger change in current. And this is probably due to the circular structure instead of a linear polymer. So when you have a circular piece of DNA going through the nanopore, you would have 4 strands of DNA instead of the 2 strands that's in a regular linear fragment. Similarly, for linear fragments, we have these 2 right here, with this one in red being a shorter fragment and the one in black being a longer fragment, which is reflected in that longer dwell time. And then I also have the data for the ribosomal detection. So there are a few key classes of results here. The ones in box A, we interpreted as being intact ribosomes since they were larger, and then things in box B would have been smaller particles, which we actually think were ribosomal fragments. So we thought that maybe we had some issues with the buffer causing that precipitation, which allows us to not only analyze the exact intact ribosomes as well as fragments themselves. So if you'd like to hear more, please come talk to me at my poster. I'll be at number 19, which is kind of over by the window. Thank you all.